To create the cycling power meter, we implemented two strain gauges on either side of the crank. One strain gauge would measure the strain the crank experiences when you push on the pedal, and the other vertical strain gauge would account for temperature changes. These strain gauges were connected in a Wheatstone bridge to an amplifier shown here to amplify the signal, and as well as the strain to measure the weight that was put on the crank. The cadence is also needed in order to get the power, and that was accomplished through the use of an accelerometer, which when positioned on top of the crank could measure the g-forces at 9.8 at a certain point during each revolution. And as well, a temperature sensor was attached, shown right here, along with the analog to digital converter to read the temperature sensor. And this is to show if there are any changes in the power readings according to temperature, as strain gauges are known to change their readings with different temperatures.
So here is how the code works. So first we need to import all the needed libraries and the class that we are utilizing that we found online to help us read the amplifier. And next we need to establish the accelerometer class. And we initialize the X, Y, and Z and the magnitude so we can get these later in our code. We also included a plot acceleration function in the class so that we could also send in all of our values and possibly plot our acceleration. Next, we incorporated our temperature sensor class so we could get our Fahrenheit temperature for temperature compensation just in case, and we also included a plot temperature function as well. So moving on to the main code, we need to first establish the pins, and so we have our data pin here and our serial clock pin. We also need to set the mode to BCM numbering for GPIO, and then we need to incorporate our HX711 class, and we need to create an object for that. And we send in our data pin and our serial pin, and we set the channel and the gain, which is needed information for reading through the amplifier. And this is just more of some of the functions that we send to the class to set all of that stuff. And then next we move on to getting an offset value, which we've hard-coded in here. We didn't have enough time to incorporate the extensive code of initializing your strain gauges. So we hard-coded the offset in, which is with no load, and then the ratio is calculated by recording with a known weight. On a crank, we used a water bottle in this case, which we weighed on a scale to get the value there. And then we set the ratio in the class, and now we can move on to recording data. So first we need to zero our arrays, get them empty, filled with zeros that we will resize later in our code. We need to create our sensor objects for the accelerometer and the temperature sensor, and now we can start our looping. So first we need to set the time and the count, and we decided to take 30 seconds data, so this is what this while loop here is for. Then we created another wait array, which would help us, we would read the strain gauges and store into this wait array, and then average it to then store into the watts array. And so we created another loop because we wanted to average our values per one revolution of the crank, and this is what the loop does here. So we placed our accelerometer parallel to the ground so the z-axis faces up. So when it reads 1g, 9.81 meters per second squared, this is when the loop will break after reading all of these values, and we will move on with our code to then calculate our RPM, our average weight, our temperature, and our time in one revolution, and we'd store these in the arrays, which we would then use to calculate our average power later. And we also did a sort for our RPM, rate per minute, just to get rid of some arbitrary values. It is very hard to pedal at 150 RPMs, trust me. Next, we calculate our power. So first we get the torque, average weight, times the radius, which is the distance from the pedal to where the strain gauges are located. We get our angular velocity, and then we calculate our power, which we termed as watts. And then we displayed it to just debug, and then we plotted our values here. And we also did all of this in a try except loop for any errors.